Which one is it? Just start guessing. And we can deduce it. Guess one. Guess one. You're Andy. Guess one. Because what type of interaction are we talking about? Are we talking about vibrations? Are we talking about electron distribution? Vibrations is in the infrared.
We're doing rotation.
We're doing rotation. So is this more energetic or less energetic? Right? Talking about spin, so it's less energetic than a vibration. Much, much less energetic than changing the electron distribution, which is in which range? UV vis, right? So we've got to drop down this energy scale. And are we talking about the whole molecule rotating or individual nuclei rotating? Which one? Which one? Pablo, which one? What's spinning in this? You just had an animation of it. It's a nuclei, right? So is that going to be more energetic or less energetic than a whole molecule spinning? Much less, right? Okay. So not talking about the whole molecule spinning, which was, again, kind of IR. We're talking even further down in energy. Well, what's radio waves, right? What else could you guess? Pretty much, right? Radio waves. Okay. Organic compounds consist of what elements? Sandy, what elements do organic compounds consist of? Carbon, keep going. Oxygen, and a whole lot of everybody?
Nitrogen.
Not nitrogen. Hydrogen. Jeez. Okay. Hydrogen atoms, Rob, are basically what subatomic particle? Hydrogen atoms, well, that's a good guess. Electron, so that's half of it. The other half would be proton, right? Okay. So I guess what subatomic particles, right, would be electron or proton, right? We're going to be interested in, well, you can see right here, protons, right? If you could distinguish all the protons, Sandy, present in an organic molecule and determine where all the protons are in the molecule, could you deduce the general structure of the molecule? Yeah. Right? 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 Yes or no? You agree?
Yes.
Okay. So for this reason, blank NMR is perhaps the most common type of NMR spectroscopy. John? Proton. Yeah. A proton is charged and it spins. Alice, you can't stop the spin. From physics, any spinning charge behaves like a... We just had an animation of it. Magnet, right? Okay. Let's jump up to the top here. What happens now? Neodymium, that's a very extremely strong magnet. They're the kind where if you get one, you put it near metal and just slams on there, your finger hurts, right? Okay. When it's placed in a uniform magnetic field, what happens? Let's see. So it's over here. Yep. Well, what's going to happen? It's going to float, right? Now, this is where I wanted to get this started, but I didn't have time. It's not easy to get this going here. I may not be able to get this. I should have done it before. Yeah. I'm going to have to get it started next time. It's going to float. Okay. And I'll have to show you that. It's hard to get it going, and I just didn't get it going for a class. So hopefully, all right, next class period, have it going when you walk in. So anyway, being roughly the size of an electron, a spinning proton, micromagnet, in a homogeneous magnetic field has blank energies, which is quite unlike the neodymium magnet that you have to imagine. Has what energies? Here's your hint. All right. So you have this guy sitting here spinning, right, or floating, right? And I could spin it any speed I want and be playing around with it. That was the idea, but it's not the size of an electron. It's the size of a big neodymium magnet. Something the size of an electron has what energies? Quantized. Right? Quantized energies. So electron, microscopic, quantized energies. That's quite unlike the neodymium magnet, right? Okay. Well, why is it different? Because an electron is tiny, yeah, extremely small. Right? Anything than that small has, in that realm, whole different realm. In fact, a proton in a homogeneous magnetic field has only two possible energies. Can you describe them? Which is the ground state, which is the excited state? There's a diagram of it. So you have this electron. Can't stop the spin. Acts like a little magnet. Yeah, lower energy would be the ground state, but why is one lower energy, the other one higher energy?
Because the north and north are playing together, so it's all like, hey, I don't like this.
Yeah, it's that repulsion idea, right? The point is that there's nothing in between. There's nothing in between. It's not like a little spinning levitron magnet I can give whatever energy I want. And that. No. There's only two. Okay, there's only two. Okay, so there's an excited state and a ground state. That's it. Nothing in between. So far, we've ignored the effect of spin on the overall motion of an object. What happens if we spin the neodymium magnet? Well, it's in its magnetic field. Okay. I have to show you this. It'd be hard to see it with a levitron anyway. It's easier to see it. Okay. So we're talking about overall motion. So you take a look at this object. All right. Get him to spin. All right. Can I see the overall motion? Not just a spinning wheel. It's doing this weird thing, isn't it? Can I get that to stop? Stay here. No. Right? So, what is that called? It's in here. It's the next one. Precession. It's called precession. And the diagram is trying to show it, right? That if you have a little tiny spinning particle, yeah, it spins, and energy is quantized, but there's few things, and I wish I could start making a list of these, where macroscopic and microscopic worlds behave the same. Here's one of them. You can't stop the precession. I can spin at whatever speed I want, so that's kind of different. And I can hold that at whatever angle I want. That's different too. But other than that, at least there's precession in both worlds. Okay. Well, think of it this way. It's a different type of momentum. It's kind of like saying if you gave a football player a whole lot of energy, I mean even more, and spun give him a whole lot of energy to go, is he going to change direction on you? No. So just like a spinning wheel, if you spun it super, super fast, even faster, it's the same idea. You have to use angular momentum. And this is going to stay rock solid in that angle and at that speed even harder, right? It's a different type of momentum. Okay. Can it be stopped in the macroscopic world? No. Is that spinning? Right? Can it be stopped in the microscopic world? Precession. No. You just have to deduce it. All right? You just have to guess. Right? It can't. Okay. We're getting somewhere here. So here's a little, this is, it also does this with a little spinning top, but it goes spinning off the table and it makes a big to-do. So it's a lot easier just to use a bike wheel. But anything spinning will precess, right? Can't Can't stop it. Here's some pictures of it. Right? Okay. What are these lines? Look at these arrows. And they have a length and a direction. What is that? What is that representing? Adriana, what is that representing? Of what type of momentum? Of, starts with an A. Magnitude of what type of momentum? Angular momentum, right? Same thing. I mean, physics is physics. It's not going to be different in PChem and in an instrumental, right? So this is angular momentum, right? Okay. And they even have it pointing in the right direction. If you remember your right hand rule, right? It's rotating.
So there is
All right. Okay. All right. See how it's... Okay, let's take a look at this. According to figure 19-1 above, a spinning proton has two energy states when placed in a magnetic field. The energy states are separated by, here's an equation for it. Gamma is referred to as the magnetogyric ratio. What would you guess? Ashley? Same or different for different elements? Different. Different. Right? Yeah, otherwise it wouldn't even be there. Exactly. There's no point for it to be in that equation if it's not different. Okay, H is whose constant, everybody? Planck's constant. B naught represents something. B naught. There's a hint. You can see it in the diagram. It defines it.
B naught represents the applied.
The applied
Energy?
what type of field? Magnetic field. If you want to have these little spinning magnets move around and interact and jump from one state to the other, it's magnetic field. So it's also written up here, right? Okay. So over here, right? Okay. So yeah. Okay.
No wonder we're going so fast. This is like 4 pages.
B naught represents the applied what? What was it called?
Oh yeah, 6.
Magnetic field.
7. I don't know.
Classical NMR absorption event would consist of a spinning proton precessing Pablo about its axis of rotation. Then a blank field is applied. They're going to call it B naught. What? Magnetic field. And the spinning proton does what, Ricky?
Hold on. It tips over.
Tips over. Yeah. Right? Okay. How many states does it have?
2.
2. Right? So within its ground state, apply magnetic field, tips over. Now you can't just apply, just any magnetic field won't work, right? Don't things have to match? Yeah, things have to match. You can't apply any field you want. Okay. So they're trying to show the angular momentum is now going in the opposite, right? But they keep the precession thing going, right? They didn't just flip the arrow over, right? They kept the precession idea going because you can't stop that. So it could go the other way too. You can go back to its ground state, but then it would emit. What would it emit? What type of light? What region of electromagnetic spectrum? Ultraviolet? Radio wave. How did it get there in the first place? It absorbed radio wave. What frequency would it emit? Does it have any choice? It absorbed. Here's its ground state. There's its excited state. It absorbed. It emits. Would it be the exact same frequency? Yeah. Right. Yeah. It absorbs, emits. Right. Are there any vibrational ladders to make things confusing and internal conversion and phosphorus? No. right? We don't have any of those modes. All we have is a little tiny spinning particle, which has how many states? 2. So it emits, it's going to emit the exact same frequency. Okay. Therefore, for a nuclei to absorb a photon and make a transition between energy levels spaced by delta E, the photon energy must exactly equal. Oh, we skipped this. In past chapters, we said the energy of a photon of light could be written as h nu. So Sandy, therefore, for a nuclei to absorb a photon and make a transition between energy levels spaced by delta E, the photon energy must exactly equal. Right? What has to match?
It's Planck's new thing.
Right? They have to match, don't they? H nu, you could rewrite that whole equation and stick it up there if you want. All right? So you could write all this up here if you want, but okay. So that photon energy, that delta, they have to match. So if we take a look at that, John, compare those two equations, should frequency equal?
Manipulate the equation.
There's really no manipulating, just erase the what? Just erase the, right? It's h nu. So, right? Make sense, John?
I was going to say, change the E divided by H, no? Or no?
Just h nu. So pull out the h. So the frequency's got to be gamma b naught over 2 pi. Right? Everybody with me so far? Okay.
What's that on top? The Y thing? What's that?
The gamma.
Oh.
Well, you can call it gamma. We're supposed to call it. We're supposed to call it what? Magneto-gyric ratio, right? Magneto. I shouldn't have called it gamma. It's the magneto-gyric ratio. Okay? Magneto. That's a good show. This frequency is referred to as the blank frequency. This was definitely a bold word. Now, there's the same name of an author who makes these lovey-dovey country western books.
What?
I think so.
Romantic country novels?
Lar
50 Shades of Grey.
L'Amour. Right? Sorry. I think isn't it L'Amour? No 2 R's. L'Amour.
Oh, no, L'Amour.
L'Amour. Isn't it L'Amour?
No.
It's not L'Amour. It's L'Amour. L'Amour. Frequency, and it is not only the frequency of the photon of light necessary for the transition. So this frequency right here, this is that frequency is called the L'Amour frequency. It's not only the frequency of the proton of light that we've been talking about, necessary for the transition to occur, but also equals the frequency of precession. Okay. Okay. Terminology, general concepts pertaining to FT NMR. FT NMR. What does the FT, Alice, stand for? Fourier transform. How do you spell Fourier? F-O. 4, and then I-E-R. Fourier transform NMR spectroscopy. How about the NMR part? What does that stand for, Adriana? What does the NMR stand for? Nuclear magnetic resonance. How come, Emily, you're not in here? Okay. With FT NMR, instead of a continuous bombardment of RF energy, what's RF? Radio frequency, right? That's the region of the electromagnetic spectrum we're interested in. Right? It's the only region. with NMR. Instead of a continuous bombardment of RF energy, the RF energy is pulsed, as shown below. So they're going to send little pulses of it. Okay? So then inside each pulse is actually a sine wave. Okay? So that's really what... Okay. So this is what the FT NMR is doing. So this is sending out this this RF pulse of energy. Let's see what it's doing with it. Nuclei absorb the RF energy, then emit RF as return to their ground state. Right? So the nuclei that match, right, that exact frequency will absorb, and then they'll go back to their ground state. This emitted signal, this emitted RF energy, is referred to as the FID. Definitely not that, right?
That's why we're all kind of like, what?
What does it stand for in NMR? Free induction decay. Free induction decay. Okay. So the little spinning charged particle absorbs energy, right? Then it emits it. Right? A single FT NMR event. So let's take a look at just exactly what's going on. In little a, Pablo, the spinning nuclei is in its what state?
You have two choices. We said them both.
It would make more. You're gonna notice look at the rest of the diagram. Deduce it. There's nothing to memorize here. Right? In A, what state is that spinning nuclei in? Take a close look at what's going on here. You have the spinning little nuclei. That little arrow, the blue arrow, never disappears, right? So it's always spinning. You can't stop the spin. Does this B naught? What's this B naught? That's the applied magnetic field, right? Does it ever turn off? No. So just a big picture on what's going on here, right? What happens in B? What happens in B?
It's like a line or something?
What's now introduced that wasn't in A? What's B1? Another magnetic field. Little arrow means what? Look at that. It's starting to move down, right? It's starting to move. So in A, everything's hunky-dory. This thing is in its what state? Ground state. All the little nuclei are, right? Let's think of the magnets. All the little miniature microscopic magnets are all lined up. They're all in their ground state, right? Because that B naught never shuts off. What is B naught? It's the applied magnetic field. Is it applied the entire time for this FT NMR event?
Yes.
Yeah, never shuts off. In B, C, and D, do you see a second magnetic field applied? B, C, and D. You see it?
B1.
Yeah, it's B1. In fact, it's applied at what angle?
45. No, it's like 60.
90, isn't it? 'Cause we're looking at
It's applied at what angle to B naught? 90. So you
Three-dimensional graph.
right? So they call it a 90-degree pulse, right? Because notice how B1 disappears, so that must be our pulse, right? Our applied magnetic field is just, a magnet that's on. Okay. What effect does this second magnetic field have on the orientation of our spinning nuclei? What does it look like? What does it have on the effect? All right. Here's our spinning nuclei in its ground state. Apply a magnetic field, and what happens to it?
Changes.
All right. this little, right? Right? Now I can hold this guy whatever angle I want. All right? That's not the case for a little spinning electron, but all right, look at it. See how if you want to see the direction of motion, the direction of spin, you have to actually stick your thumb in the direction of the little blue arrow, right? But it looks like it flops over, right? Okay. Let's keep going here. Yeah, what effect does it have on the orientation? It
Just
changes it, turns it, whatever you'd like to describe that, right? Flops it. Yeah. Okay.
It does what?
And then you get to E1.
It does this.
Right? And then you get to E. In E, B1 equals what? 0. So it just got shut what? It just got shut off, right? The pulse is done. You reach the end of your pulse. Okay? And the magnetic field, right, in B1 equals 0. So now things are going to return back to their ground state. Okay? So it's in its excited state. By the time the pulse is over, it's in its excited state. Right? Because it can only go one place or the other. It can't be in between. So as it returns to its ground state, it emits. It's at a higher energy. So it can only emit. And what type of energy does it emit? Radio waves, right? The frequency of the RF energy emitted by each spinning nuclei is its, what do we call it? Frequency? Well, precession frequency, but we gave it a name, L'Amour, right?
I want to know where they're getting 90 degrees when they say 90 degrees for the
90-degree pulse. Look at this guy's going here. This guy's going. Look at it three-dimensionally.
This is an x-axis, y-axis, z-axis. It's just
All right.
Oh, okay. I was looking at this angle right here. I was like, that don't look like 90.
No.
All
right. Okay.
Kind of.
Once the FID, the free induction decay, is obtained. So what is that free induction decay? It's just a RF signal, right? And it's just getting weaker and weaker. Why is it getting weaker and weaker and weaker? Why is it decaying? Because all these little spinning nuclei are ending up where? In the ground state. The signal can't go on forever, right? It's going to start out really intense and then it's going to die off. But you have all these different, right, nuclei decaying. The little RF signal is just decaying. It's kind of like if you could imagine phosphorescence and just sitting there for 3 or 4 minutes and the whole thing just dying off. Right? Okay. Once FID is obtained, a Fourier transform is applied to the FID. What Fourier transform does, it just converts from one domain to the other. In this case, we're converting from the, what domain is this? What's this axis? Time, right? Well, time or seconds, right? To frequency. It's converting from the time to frequency domain. Big deal, because then you can, right? Because once you get into the frequency domain, you can associate frequency to bonds and a lot of different chemical properties. And we'll get into that a little bit. So I convert the time to the frequency domain. So that free induction decay, right? This is converted to this frequency domain. And it just consisted of essentially, looks like 1, 2, 3 frequencies. This signal did, if you apply the Fourier transform to it. Okay. From the frequency information, we can determine the chemical environment of different nuclei, in this case protons, and even their respective number. So I'm not expecting you to see this. The point is you can see different like CH3O, I mean HC double bond C, that has a different environment than HC triple bond C, right? And they're just trying to say that all these different chemical environments of a proton, they each have their own frequency. Why do protons in different chemical environments absorb and emit different RF frequencies? A proton's a proton.
Magnetic gyro.
Another one to be.
They're in a different magnetic field from each other. Does that happen?
Okay, we're getting there. Someone said, okay, here's our equation. All right, here's our equation that we're supposed to, that's the hint. Now, would it be, something in here has to be different for these protons that are in different chemical environments. Is it the magneto-gyric ratio?
Yes.
Where you said that it was different.
For different, what? Gamma, magneto-gyric ratio is different for different, what? Different for different elements, right?
Oh, but we're all looking at the same one.
What element are we looking at? H. Exactly. So you find the magneto-gyric ratio for hydrogen, put it in there. That's not going to change on you. Planck's constant, can he change? 2 pi, can he change? Obviously. It must be this thing, this applied magnetic field. Well, how the heck can that be? Okay, we're getting somewhere. You have a proton. All these organic molecules have, a lot of hydrogens, but they also have a lot of what? Well, yeah, we're thinking about the electrons, right? What's the other charged particle that's present? And there's a lot of them. Electrons. Do electrons have a charge? Do they spin? Yeah. So they're going to act like little tiny what also? Little tiny magnets. Well, if Pablo's a magnet, right? We're all magnets, right? And there's this big ass magnet outside. We're going to be, and he's trying to sit Adriana right in the middle. We're all going to feel different magnetic strengths because some of us are going to block it, right? And shield is the word, right? And so each different chemical environment really leads to different fields that they feel, right? That nuclei feels. So that's kind of what's going on. Back. Yeah, B naught is different. This table is really what it is, oh man, I feel like a bare proton, no one's shielding me. That would mean there's hardly any what around? Electrons. He's going to feel the full B naught, right? Oh man, I don't feel hardly anything. Well, then you're surrounded by a whole heck of a lot of electrons, right? A whole lot of methyl groups. Okay. So you go way down here, down to the bottom, and you start seeing a lot of C double bond OH, and look at all these oxygens and stuff hanging out down on the bottom. Up on top, well, we're going to see methyls and TMS at the very top. We'll see what that is. Okay, so just two ends of the spectrum there. Environmental effects for proton NMR, there's two types. Okay. Because if this didn't happen, there wouldn't be any spectroscopy. Everything would be the same. So this is what's going on and why we can actually get some information out of this. There's these environmental effects, the chemical shift. Different protons in a molecule, Ricky, feel different applied magnetic fields because electrons blank the applied magnetic field.
Whoa, where is this at the bottom? I was looking at like that lower, higher. Oh, okay.
You're Andy? You're Andy?
They shield.
All right? They shield. Okay.
I was looking at the one right below that.
Okay, we're following from top to bottom. That's how we always handle this, okay? The applied magnetic field. So protons in a part of the molecule with a lot of electrons actually feel a, you're Andy, Lower, higher. So you have protons in a part of a molecule with a lot of electrons around them. They actually feel a what magnetic field? Lower, right? Because there's a lot of electrons on. There's a lot of shielding going on. You're not going to feel as strong a magnetic field. Okay. If a chemical shift were the sole environmental effect, we would expect to see individual peaks in all NMR spectra. The individual peaks would indicate the different chemical environments. And the bigger the peak, the more protons, right? So you'd have, okay, we have all the methyls. Now, okay, that's always this frequency. Kind of like what this is saying, right? And you say, oh, okay, you line up wherever your little frequency is. You use this little funky chart. Okay, fine, they have weird units like parts per million and stuff, but it's the same idea. Just look at the frequency, and you can tell exactly what's there. Oh, this functional group, that functional group, this functional group. Okay? But you wouldn't really know where those functional groups are on the molecule. So there must be another type of effect here. Because otherwise you just know, oh, okay, I have got an OH group, and I've got, I don't know, an amide group, and I've got that, right? But where are they at on the molecule? There's got to be another type of effect that answers that question. And there is, right? Whoa, went too far. There it is. Environmental effect number 2. Spin, spin, splitting. Magnetic moments of protons interact with each other. Since magnetic moments interact with one another, we don't get these individual peaks. For different chemical, we don't get individual peaks for different chemical environments. Instead, we get split peaks. So the thinking is close. I mean, if you have a methyl group, oh, here its frequency is over here. If we have another type of group, oh, it's over here. That's right. But these peaks are actually split depending on what's going on around them. Okay, what protons are around them. Let's take a look at this. Ethanol. Why they call it the N+1 rule. We'll apply it. Ethanol. The chemical formula for ethanol. CH3CH2. Everybody? OH. Okay. How many different groups of protons would you expect? Rob, how many different? So you have these, I see 3, 5, I see 6 protons total, right? And I guess, are all of those, these 3, are they all chemically equivalent? Do they all have the exact same chemical environment? Why? What's so special about, what type of bond is that between the methyl? Yeah, covalent, but is it single, double, triple? Single. Single bonds, can they rotate? Yeah, very easily, right? So this methyl, he's just sitting there spinning around. Same with the CH2, sitting there spinning around, right? So it looks like there's how many different? There's 3 different H families. Good, all right? There's 3 different chemical environments is the best way to say it for protons. 3 different chemical environments. Can everyone see it? Okay. So, oh, we just answered that one. All right. Okay, Emily, how about which group exhibits the most shielding? Yeah, I mean, which group, right, is going to actually feel the least? He's got the most electrons hanging around him. It'd be the methyl, right? You've got, I don't know how else to explain it. But we go to the opposite spectrum, the least. It would be the OH, right? There's nothing out there protecting that hydrogen on that OH. Just a bare proton. Okay. If solely chemical shifting occurred, sketch a proton NMR spectrum of ethanol and identify the different groups. Include a TMS peak in your sketch. So let's just, we haven't talked about TMS yet.
That's like the most shielded, right?
Exactly.
So you just go from the left is the least shielded to the right.
There you go. That's the thinking. TMS is a tetramethylsilane. extremely well shielded. And we'll talk. I think that's the next screen. But so you go from the least to the most shielded, right? So you'd have maybe now OH only has how many H's though? One. Area under the curve really corresponds to the number of protons. So I don't know, you'd have to be pretty good at this to do this, but you'd want that area to count as 1H then, right? And then the next would be the CH2, so this is my OH. My CH2, you want twice the area. I don't know, is that twice the area or more? Right? And then CH3, you want 3 times the area. I don't know, right? I don't know if that's mathematically correct, but that's the thinking, right? 3 times the area of the OH. According to the n+1 rule, a peak is split into n+1 peaks. N is the number of identical protons adjacent to the group. So taking both chemical shift and spin splitting into account, sketch a proton NMR. Okay, so we have this TMS thing. Don't worry about him. We'll talk about him later. There's our TMS. Okay, let's identify that methyl, the CH3. How many identical protons are around the CH3? No, sorry, adjacent to. Adjacent to it. Adjacent to that group. So how many identical protons are adjacent to the CH3? That's a better question. 2. So you have to be split. So my little n is 2. So where is it? N+1. So I'd have how many peaks? 3. So split that methyl peak into 3 peaks. And you want the area, again, to be kind of consistent, right? So split them into 3 peaks. 1, 2, 3. All right. Give it a lot of area. The CH2, now you want this to be the same spot, though, right? You want that to be the same spot. The CH2 has how many identical protons around it?
3, 4.
Now, it has to be adjacent, though. That's too far. It has to be adjacent. So it's only going to be...
Isn't it just as far as the methyl? Yeah.
No, you have an O there. That H has an... What's adjacent to the carbon, to the CH2?
That still makes it. Yeah.
Over here and over the O,
Yeah,
right? So it's too far.
Yeah.
It's too far. So it's just going to be the CH... Right? There's 3. There's 3 identical protons right next to them. Right?
Isn't it just C to C, C to O, and then one more pH each time?
Yeah, no, the O is in between.
Okay. So carbon.
No. Just get used to it. Get used to it.
Okay, so
Right?
we're just going to ignore O forever and always?
It's it's too far. Right? There's 3 identical protons, right? N+1 rule. 4, break them into 4. Okay? No? Yeah, well, everyone has their own way of looking at it. All right. Ah, it's too much area.
Yeah.
Okay. In the OH group, I'm looking at more. Don't worry about it.
I think you just ignore it.
OH group,
Sorry.
the H just
by itself.
just by itself, according to Smith's rules, right? Now, everything's going to change though the stronger your magnet,
Yeah.
and then you're going to get more stuff. So this is as simple as it gets, right? And I'm simplifying life probably a little bit too much for you, but the wrap-up ideas. Internal standard is added to all proton NMR samples, called TMS. There it is. Tetramethylsilane, 4 methyls. Why is this compound chosen as the internal standard? To measure all proton chemical shifts from? Because then we can just measure A. Right? Once you know where he is, then it doesn't matter whose instrument, where you're at, you're going to measure all changes in frequency from TMS. So it doesn't matter whose machine you're using, how much one dude spent on the other. Ooh, I've got a better magnet than you. It doesn't matter. right? Ooh, the strength of your magnet is superconducting, ours isn't. No, we're going to measure it with respect to TMS, those changes. Our FT-NMR is a permanent magnet. Researchers use a much more powerful magnet, superconducting, which can erase credit cards, all that kind of stuff. What is the benefit of using a more powerful magnet?
Interrupt pacemakers.
It's a benefit.
All right? What is the
Well,
benefit?
it splits the signals to be further apart.
Further apart, big time, right? It's resolution. Resolution is the key. Just this thing would get whoosh. Okay. So with ours, we can do some simple things, but we don't have the resolution to do. All the simple stuff has been done if you're talking about research. Okay. When obtaining an NMR spectrum, resolution
That's a disadvantage?
is an advantage.
What?
Okay, so what's the disadvantage?
Where does that ask that?
Are there any
Expensive as hell.
disadvantages? Yeah, that's the
Oh, okay. Yeah. Well, expensive. Oh, good. Okay. What are these big? Why is this so? What's this big? I can't really see it too well. But look, there's a chain around there.
Oh, is that to keep
All right.
company
Credit card, right? Do with pacemaker. So you got to be. That's a disadvantage, I think. But for me, but so what? You put up a chain, and if people walk by it, just have a little. I don't know. I don't know.
Have a little sign at your own age.
The room's got to be locked up, and so there are disadvantages there. But I think the real disadvantage is it's hard to see the little tubes and vents here. It's kind of seen over here, though. For these superconducting magnets to work, for you to get that strength of a magnet, it needs to be really, really cold. It needs to be really, really cold. Liquid nitrogen, essentially, or liquid argon. It's something that makes it really, really cold. So you got to constantly be pouring in liquid nitrogen. Okay. Oh man, we went way over today. Yeah, well, last question. When obtaining NMR spectrum, we have to make sure the sample is spinning. Why?
So it's like a magnet?
No, the sample.
Oh, okay.
If you don't have it spinning, I mean, nothing changes. Nothing changes. You have your little nuclei in the ground state, the absorb, right? Nothing, pre-induction decay, nothing really changes. The problem is that you don't have your applied magnetic field needs to be uniform, needs to be homogeneous. And if it's not, I mean, you're going to get different applied magnetic fields all over the place because it's not uniform. So that's why they spin it, to have a uniform, or homogeneous is the word. Okay. So sorry we went way over by like 8 minutes here.
Why does it say the sample needs to spin?